Okay, hello everyone, and welcome to the Bite-Sized Bioinformatics talk today, which I'm going to be doing on equivalence testing, is what it's called. But this is basically looking at statistics that you can do when you want to show that there is no difference in your data. So I thought the best way to start off with this is to go over some basics of statistics to start with, and what we usually do in these situations. So for the sake of this talk, I'm going to use the term hypothesis testing for when we are wanting to show that there is an effect. So this is our usual testing that we do. I'll then use equivalence testing for when we want to show that there is no difference, even though it's still sort of hypothesis testing, but just for the sake of not having super long names for these things. So hypothesis testing, usually we want to show that there is an effect in our data. So usually we want to show, for example, that our knockout is different from our wild type, or that our treatment has an effect compared to a control, whatever other question we might have. And to do this, we use hypothesis testing. In this case, we have what we call a null hypothesis, which is our default state that we want to test. So we want our null hypothesis is that there is no effect. This is effectively our innocent until proven guilty state. And with hypothesis testing to show there is an effect, the aim of the statistical test is to reject or not reject our null hypothesis. And this basically means that we can have these 4 outcomes from this. So on the left here, we have the statistical decision that we have. So this is reject or not reject our null hypothesis. And then on the columns here, we have the true state of the null hypothesis. So this is the state of the null hypothesis in the actual whole population. We don't actually know this usually. We use our statistical decision to make our best guess of this and hopefully control the false conclusions that we might have. Basically, the 4 outcomes we can have is a true positive if our null hypothesis is actually false and there is an effect, and we reject our null hypothesis. We can obviously have a true negative if the null hypothesis is true and there is no effect, and we don't reject the null hypothesis. Then we can have our 2 different types of error. So we can have our type 1 error, which is also called alpha, which is our false positives, when our null hypothesis is actually true and there is no effect, but we reject our null hypothesis in our statistical decision making. Or we can have our false negatives, which are our type 2 errors, and this is called beta, which is where our null hypothesis is false and there is an effect, but we fail to detect this and we don't reject our null hypothesis for our statistical decision. So I'll go into these in a little bit more detail, but that's just a very quick overview of what we usually look at and our usual outcomes. So a little bit more detail on these. So with hypothesis testing, we start, as we expect, with a hypothesis. And we actually have 2 of these. We have our null hypothesis, which is what I was talking about on the last slide. This is the thing that we either reject or don't reject. And this is, in the case of our normal hypothesis testing, the absence of an effect. So it could be, as an example, no difference between our control and our treatment. The other hypothesis we have is our alternative hypothesis, and this is the presence of an effect, so that there is a difference between our control and our treatment group, for example. So we have this potential difference that we want to test for. So there's a few statistical steps that we have to take in order to test this. The first thing, well, the first couple of things we often don't really think about too much, but the first thing we really do is set a significance level, or alpha. Usually we just use 0.05 or 5%. This is generally convention. But what this actually means is that our probability of making a type 1 error, which is claiming an effect which is not there and rejecting a true null hypothesis, the probability of doing that is 5%. The other type of error that we can get is the type 2 error, and we try to control for that by doing a power analysis, which is effectively the same as setting our beta for our experiment. Usually our beta is higher than our alpha at 0.2 or 20%, and we get this as our power is 1 minus beta. So usually we set our power at 80% to give us a probability of making a type 2 error of 20%, or of missing an effect that is really there for more understandable terms. Then we go off and we do our experiment and we get our data, but we're not interested in that today. So then we look at determining our statistical significance. So we use all of this that we've done previously, and we compare our alpha, which we set at 5%, and the p-value, and we determine whether there is a significant difference if we reject our null hypothesis, if our p-value is less than 0.05, or if there is no significant difference if our p-value is greater than 0.05. A note that the p-value is actually the probability that the observed statistic occurred by chance alone, or in more reasonable terms, the probability that a difference as big as the one that we saw in our experiment could be found even if there was actually no effect in the wider population. I have a few things to say on this, coming back more to equivalence testing. The first point is that down here, when we say that we fail to reject our null hypothesis, this is not the same as accepting our null hypothesis. So we can't say if our p-value is greater than 0.05 that there is actually no difference. We just can't say that we can show that there is a difference. And this is obviously really important when we're looking at equivalence testing and showing that there is no difference. And one of the reasons why this is important to remember is sort of going back to our type 1 and our type 2 errors. So in the case of equivalence testing, we're sort of effectively swapping our null and alternative hypotheses. So in effect, we're making our type 2 error sort of our type 1 error. And our type 2 error is always, or generally set at a higher level than our type 1 error, because that's thought to be a sort of less bad error to come up against, missing an effect rather than claiming an effect that isn't there. So this is why we want to use a different approach when we're doing equivalence testing compared to just saying, oh, there's no significant difference when we're looking for an effect, so I'm going to say that there's no effect. This is also all in the case of properly powered studies where we have done our power analysis and we do know that our type 2 error is set to 20%. Obviously, this gets worse if we haven't properly powered our studies as well. So, quick overview of hypothesis testing. Again, the null hypothesis usually is that there is no effect. And the aim of the statistical test is to reject or not reject our null hypothesis of there being no effect. It is not to accept our null hypothesis, which is why we need a different approach for equivalence testing. So, equivalence testing. Why would we want to do this in the first place? It's when we want to show that there is no difference. So often this is in sort of pharmacokinetic studies and things like that, where we want to show that a new treatment is as effective as an existing treatment. That's sort of where it's come from originally and where most of the equivalence testing you see is done. But we could also use it, for example, if we're looking at whether a treatment can basically make our knockout equivalent as the wild type. So there are just a couple of examples, but obviously there are a load more other examples where we might want to do equivalence testing. And as I said before, the null and the alternative hypotheses are basically switched. So our null hypothesis is now that there's no difference, and our alternative hypothesis is that there is a difference, and our alternative hypothesis is that there is no difference between the groups. Another slight note on equivalence testing is that there is essentially a directional version of this called non-inferiority, which is usually used in pharmacokinetics again. So this is when you want to show that a new treatment is no worse than an existing treatment, but you're not actually interested in whether it's better. So this is the equivalent of doing a one-tail test versus a two-tail test in normal hypothesis testing. But that's just in case anyone sees about non-inferiority. It's a similar kind of concept, just directional. So in terms of equivalence testing, how we actually do it, there's two main approaches that I'm going to go through. We have the two one-sided tests, or TOSs, and the confidence intervals, which are sometimes called CI. The biggest challenge that we have with both of these approaches and with all kinds of equivalence testing is that we have to set equivalence boundaries. So this is a window within which the groups are too different to be considered equivalent. This is scientifically determined. It's sometimes also called the zone of scientific or clinical indifference, which I quite like. That was on the PRISM website as well. But that sort of shows what we're interested in this, which is that it's the maximum difference that's not large enough to make a practical difference. So if there's a 10% difference, maybe that will have no biological or clinical effect. And so if there's like a 5% difference rather than a 10% difference, we don't really care. They're basically the same. We're not interested in that small of a difference. It would need to be 15% to be considered sort of biologically meaningful. And this is similar to the effect size for power analysis. So when we're thinking about that, we're looking at the opposite, the minimum effect that would be different enough to be biologically relevant. So that's another way to think about it. The other slight note on this is that they can be asymmetric. So if a 10% increase would not have too much effect, but a 10% decrease would have a big effect, and actually you'd want to have a sort of 5% decrease and a 10% increase, then you can do that. They don't have to be symmetric around 0 if you're looking at differences between groups. So that's a quick introduction. I'll go through now how these actually work conceptually. So the two one-sided tests, I'll go through first. These are also called TOST. The basic principle for these is quite simple, I think quite clever, is that you do tests on both sides of your equivalence boundaries. So I've arbitrarily called these test 1 and test 2 for the sake of visualization. So test 1 will test for a difference that is greater than the lower bound. So if we look on this little diagram here, this is the difference between the groups. If they're exactly the same, they'll obviously have a difference of 0. And we've set our lower bound and our upper bound for our equivalence boundaries. So test 1 tests that it's greater than the lower bound. Test 2 tests that it is lower than the upper bound. And so we're looking for significance on both of these tests that would suggest that our real difference is somewhere between our lower bound and our upper bound, and then we consider that to be effectively equivalent, and we conclude that it is statistically equivalent based on our two-sided test. I'm again going to go back to our normal hypothesis testing to introduce the idea of how this works in a bit more detail. So I'm going to stick with two group comparisons because that's the simplest case. It doesn't have to just be two group comparisons. You can do this with correlations and things as well, but this is the easiest conceptually to go through. So in usual hypothesis testing, we use a student's t-test if we have parametric data, which again, I'm going to focus on today for the sake of ease and to introduce this as a concept. So we use a t-test again to compare two groups. I'm going to stick with the example of a control and a treatment. So we'd have these two potential populations here. So we have our control group and our treatment group. Sorry, I don't know why it keeps moving forward. We have our mean in the middle, and we have some level of variability in our two groups. And so a t-test looks to compare the two means while accounting for the variability or the spread in our data. And so this is what our t-test looks like. We don't need to worry too much about equations if we're not that comfortable with them, but basically with statistical tests, we're often looking at the difference of our signal versus our noise in our data. So in the case of the t-test, we're looking at the difference between the group means. Literally, we're looking at the mean of group 1 versus the mean of group 2. And then we're accounting for by dividing by the variability of the groups. And that's shown here. But this is basically just the combination of the two standard errors of the mean, which is a measure of the variability. And from this equation, we get what's called a t-value, which is our test statistic. And from this, we can get a p-value, which will tell us whether it is statistically significant or not. In the case of our two one-sided tests, these are very marginally more complicated, but essentially the same. So this time our signal, instead of just being the difference between the group means, is the difference between the group means minus our equivalence boundaries. So as the name suggests, and as we saw previously, we have two tests, so we end up with two t-values. The equation is entirely the same except for taking away the equivalence boundaries, the lower boundary for the lower t-value and the upper boundary for the upper t-value. So because we have two t-values, two test statistics, we end up with two p-values. And if we remember, both of the tests need to be significant to be considered equivalent. So we just report the lowest t-value and the highest p-value from these two tests, because the higher the if the highest p-value is significant, then obviously the other one is going to be significant as well. And so we can show that they're effectively equivalent. So quick summary on the two one-sided tests. The basic principle is we do a test for both sides of the equivalence boundaries. So we do first test for being higher than the lower, second test for being lower than the upper, and we need both tests to be significant to consider equivalence between our groups. So the second approach is using confidence intervals. Again, I'll start by introducing confidence intervals in our usual hypothesis testing when we're looking for a difference. There's a few things to note about confidence intervals. The first thing is that they're inferential. So we use a sample to make inferences about a population. And I've alluded to this a few times already. So our statistics are also inferential. So when we're doing our t-test, we're trying to decide whether the sample that we've taken from our population can be used to make inferences about our population and to see whether there is a difference. Usually in hypothesis testing, we use 95% confidence intervals. This is because we set our alpha at 5% or 0.05, as we all know. And basically what our 95% confidence interval contains is a range of values that we can be 95% confidence contains the true mean of our population. Another way of thinking about this is that on average, 19 out of 20 of our experiments will include the population mean, which is shown down here. So if we have a population mean as the red line down here, obviously in real life, we don't know this. That's why we're doing our experiments to try to figure this out somewhat. So if we did 20 different experiments, all from different samples of the same population, we might end up with these confidence intervals. So that's the mean of our experiment and the confidence interval surrounding it. And out of 20, 19 of them would contain this population mean. Again, we wouldn't know which experiment we've necessarily done. So we might randomly have selected quite an extreme sample from our population and ended up with this one, or we might have had quite a central one like this. But generally, when we're looking at statistics, it's looking at probabilities and trying to control how many of our results end up sort of on the edge here, and try to make sure that overall we're fairly confident in what we're seeing. Again, narrower confidence intervals mean that you have a more precise estimation of the population. Confidence intervals are based on sample size and also the variability of your data, both of which, if you have less variability or a higher sample size, will increase the precision of the estimation. So if we go back to equivalence testing, again, when we're doing the confidence interval approach, we have to define these equivalence boundaries, which might be tricky, but unfortunately are not a statistical question. That will depend on your data or on your area of interest, sorry. So for equivalence testing, we instead calculate 90% confidence intervals. And I'll come back to that in a second. But if our 90% confidence intervals fall within our equivalence boundaries, then we say that they're statistically equivalent. If they overlap or are outside of our equivalence boundaries, then statistically they're not equivalent, and we can't reject our null hypothesis that there is a difference. And this is a visualization of the confidence intervals approach. So these are just a few examples of what you could get. So you can get like experiment A and C, where you have really wide confidence intervals. And I think what's nice about this approach, and also using confidence intervals in usual hypothesis testing, is you can see these are really variable. So they might not be the most trustworthy in terms of experiments, so you might not have enough data to really answer your question that you're trying to look at with this. You can see quite visually from the confidence intervals the ones that will or won't be significant. So obviously A, B, C, they all overlap the equivalence boundary, so they wouldn't be significant. D, E, and F would all be significantly equivalent. D actually has a difference of 0 and quite tight confidence intervals, so that is really convincing. But even F, where the confidence intervals don't overlap 0, where there's no difference, they're still considered equivalent because they're within our equivalence boundaries. And so they're not different enough to be sort of biologically different or clinically different. They're just different enough to potentially be statistically different, which I'll come back to in a second. And again, the study G here, that's clearly not equivalent. It's outside of the equivalence boundaries and doesn't even overlap these. On the right here is just showing some of the other ways that you can look at this. So on here, the 90% confidence intervals are the thicker bars, and then the thinner lines at the end are the 95% confidence intervals, which is what we look at with hypothesis testing when we're looking for an effect. So there are a few different outcomes you can have when you look at both of these. So study A here clearly would be equivalent because the 90% fall within the equivalence boundaries, and it also overlaps 0, as do the 95%. B is not equivalent because it goes over the edge, and also would be statistically significant if you were doing a hypothesis test to test for a difference. C is interesting to remember it exists because you can have, in this case, an experiment where it is considered statistically equivalent and also statistically different. And this is because of the way we're defining the equivalence boundaries. So this is basically a sort of false positive statistically significant difference because it's not a big enough difference to actually be relevant biologically. And this is where we need to also remember to properly power our studies, because this study could potentially be sort of overpowered to detect. So it detects too small of a difference to be of relevance. And finally, we can have D, where it is neither equivalent nor different based on statistical tests. So coming back to why 90% confidence intervals, this is confusing, as admitted by GraphPad Prism. This is where I pulled this from. It says, confused about the switch from 90% confidence intervals to conclusions with 95% certainty. Good, that means you're paying attention and it is confusing, and that's about as much as they say. So I've tried to make put this in a way that hopefully makes sense, but it is quite confusing. So I think the easiest way to think about this is that for equivalence testing, to have a significant effect, it must be within the bounds, within that particular area. And so when we're doing our two one-sided tests, we need both tests to be significant for this to be considered equivalent. For hypothesis testing, if you have a two-tailed test, which is usually what we do, we usually test for a difference in either direction, then it can be either above or below. And so to control our type 1 error rate, usually we split our 5% on either side, as you can see down here. I think sort of the easiest way that I can think of to get my head around this is that for equivalence testing, you sort of need both tests to be significant. So it has to be both above and below a boundary. And so both need to be significant. So your 5% works for both of them. For hypothesis testing with a two-tailed test, effectively, if you think about it in a similar way, either test can be significant. So it can either be above or below and still be significant. So you want to split your type 1 error rate on sort of either side of the population. So you end up with 2.5% on each side. Hopefully that makes some sense. So that's a quick summary of the confidence intervals approach. Again, you have to define your equivalence boundaries. We use 90% confidence intervals rather than 95%. And if they fall within the boundaries, then they're equivalent. And if they're outside of or overlap with the boundaries, then they're not equivalent. So in terms of which approach to use, this will somewhat come down to personal preference. So they should give the same results because they're sort of looking at the same thing, but the two one-sided test gives a test statistic and a p-value, which we're used to seeing from normal hypothesis testing. So it sort of makes it more consistent with what we're used to, which is, I think, quite a big benefit of it. Confidence intervals are simpler. I think you can do quite nice visualization with these, and they're also sometimes the only option. So depending on what software you use to do your statistics, you might only be able to do confidence intervals without switching to something else. And I've put a note that no matter which one you use, you always want to report the equivalence boundaries used, because obviously that will affect whether or not it is significant, depending on how you came up with those. So the last part of this is looking at how we actually do this. I'm not going to go through and do any practical examples of this because I think it's actually fairly simple once you know what you're looking to do and how you might approach this. So for the GraphPad Prism people, there are no built-in tests for equivalence, but you can use the confidence interval approach. And they do have a help page on their guides, which you can find, and I've included the link. Basically, to do this, you just compare your two groups with a t-test, or with whatever test would be appropriate. You can also, at this point, include things like pairing or independent tests. So you can take into account pairing with equivalence testing as well. And then in your analysis window for your t-test, you go to the options and you can select the 90% confidence intervals rather than the 95%. That's the only difference that you'd need to change on there. The other thing that's nice with Prism is you can graph the confidence intervals of the difference between the means, which is called an estimation plot, which I think can be useful for visualizing equivalence testing. So that looks like this. It shows this is just example data. It's not actually anything, but it will show your control and your treatment as the raw data, and it will also show the difference between the means. And then you can add on, like, red lines is what I've done here for your equivalence boundaries. So I've decided that 20 and minus 20 on this. And then you can see your confidence intervals and show that it overlaps these boundaries as we were looking at before. So I think that's quite a nice option for that. The other thing that we look at is R. So there are, again, two options to do this. You can do either approach in R, as you might expect. So there is a package for this called T_tost that can calculate our two one-sided tests. This has quite a few different options. So again, you can do paired or independent tests. It also includes power calculations. So I haven't gone into that today, just because I feel like that's a whole nother can of worms. But generally, to do equivalence testing, you need slightly larger sample size than you would to test for a difference. So that's worth bearing in mind as well. Also in R, normal statistical tests generally can output your confidence intervals. So we just have to remember to alter those to 90%. So as an example, we can use the t-test with all of our usual parameters we would use for our t-test, but setting our confidence level at 0.9 and also setting detailed equals true so that it outputs the confidence intervals as well. So that is all I had on that, but hopefully that gives an overview of how we think about this and how we might approach showing that there is no difference. So thank you for listening, and I can take any questions.